Welcome back to the second session. Celebration of Enrico's 50th anniversary of his Fields Medal. Our next speaker is Jonathan Pila, who will speak on G functions, rational points, and unlikely intersections.
Great, thank you.
He's
Thanks.
from Oxford.
Great, thanks. Thank you very much. It's a great pleasure to help celebrate this anniversary. And I'd like to talk about some Diophantine problems that intersect with Enrico's work in several different ways. So I'd like to start the story in 1999 when Bombieri, Massa, and Zanya this 1999 considered the following problem, which is a problem of unlikely intersections. So we consider a curve, V, an algebraic curve, so zero set of some polynomials in the nth power of the multiplicative group. And we want to consider the set of points on this curve. So x bar will be n tuple of points such that x lies in an algebraic subgroup of codimension at least 2. So that amounts to considering points on the curve that satisfy 2 independent multiplicative conditions. And since you're putting 2 conditions and the curve is one-dimensional, any such point is an unlikely intersection, dimensionally unlikely. And so they conjectured, so that we have this set, if you like, V intersected with the union of algebraic subgroups defined by multiplicative conditions. So G is a subgroup, algebraic subgroup, C star to the n, with codimension at least 2. And they conjectured that this set is finite under a natural condition. And the condition is that V is not itself contained in a proper algebraic subgroup of the torus. That's a necessary condition, because after that you only need to impose one more condition, and then you'll intersect infinitely often with the curve. So they proved the theorem under a slightly stronger condition, that it's not contained in any coset. And in fact, this theorem, but the natural condition was proved a bit later by Morin. So let me just write is finite unless the condition I said, unless the curve is contained in a proper algebraic subgroup. Now this theorem includes the Manin-Mumford statement for a curve, because one way that you can have 2 multiplicative conditions is simply if 2 of your points are roots of unity. So then this includes that statement. And this theorem also includes the multiplicative, the Mordell-Lang statement for a curve, because if you want to now deal with finitely many generators, you can somehow extend C star to the n by some extra coordinates that you make constant. So you extend the curve V by adding several extra constant coordinates. And now one way to be in a subgroup of codimension 2 is for 2 of your coordinates to be in the division group of those fixed finite things. So this problem includes the Manin-Mumford as well as the multiplicative Mordell-Lang for curves, which is a theorem of Liardet. in that case. But it goes significantly beyond those.
The length for curves is what? Is
And
theorem of Liardet.
Liardet proved that. for
Okay.
curves. No, so then later they formulated, I've just stated this for curves, the concreteness, but this led them to consider higher dimensional analogs of this that would include full multiplicative Manin-Mumford and multiplicative Mordell-Lang. I just want to say before going into that a key point, because it's a key point that will come up at a number of points in this talk, although I don't want to go into it too much, but a key point in this was to prove that these points have bounded height. Bounded height. Maybe I just put that, I don't want to say too much about it, that even if you consider the likely intersections of a curve with subgroups, algebraic subgroups of codimension 1, that you get a set of bounded height. That's what's key to this. And this bounding heights will come up at a number of points. So this line of work led them to formulate a bit later in 2007 a conjecture, I mean, the higher dimensional analog of all of this, a conjecture of unlikely intersections. And I guess I don't want to go into, I mean, I don't want to go into that too much, but I mean, you can see the generalization that V, if you increase V in dimension, you can also consider its intersections with things of complementary -1 dimension, but you can also consider more generally intersections of V with any subgroup which have a larger dimension than you expect. That's the so that's a generalization of the unlikely intersection, which is called an atypical intersection. And the general conjecture is sort of a finite description of that. All of that has a finite description. Here it's just a finite set. So they were led to formulating this conjecture, which had also been formulated by Zilber, coming from ideas in the model theory of exponentiation and related to Shanwell's conjecture, and which were later also generalized very much by Pink, by taking the context not only of the multiplicative group or a billion varieties, but also Shimura varieties and mixed Shimura varieties. So we'll come back to that a little bit later. Now, at the time, Bombieri-Massesania's motivation came from a problem of Schinzel on reducibility of lacunary polynomials. So there was a paper of Schinzel in which he formulated as a question a kind of very special case of this problem. So that was in 1989, but at a similar time, another problem of unlikely intersections was raised by Yves André in his book on G functions and geometry. So those are the G functions. So that book was also published in 1989. So I guess I didn't want to give a definition of G functions. The G functions and the E functions were both introduced by Siegel in the context of transcendental numbers. And the E functions are functions that look a bit like the exponential function. So they satisfy a linear differential equation with rational function coefficients, and they have a Taylor series. Let's write it as an over n factorial x to the n, and where you impose some suitable growth conditions on these ANs. They can be integers, or they might be in the number field, and there's control on the heights and the denominators. And for this class, so these were introduced by Siegel. And then you have the G functions, which look a bit, which also satisfy differential equations, and they have a similar expansion with Diophantine growth constraints on these coefficients, but now there's no n factorial. So these functions have finite radius of convergence, whereas these ones are entire functions and so on. And so here you know, this is like e to the x, and this is like logarithm. And these functions arise from the period functions of families of algebraic varieties, which is what Yves André was studying. And in this book, he considered the problem of fibers in a pencil. So you consider a pencil of 1 billion varieties. So this is some curve in the moduli space of 1 billion varieties. Dimension G. And so with each point here, you have some 1 billion variety. And he wanted to consider the 1 billion varieties in this pencil, which had an exceptionally large endomorphism ring. And in particular, so he assumed that the general one, I think, had just the endomorphism ring was Z, and that he wanted to look for the exceptional fibers. And he proves a partial result that under suitable conditions, G greater than 1 and odd, and some point of multiplicative reduction, and so on, that you get finitely many points so these will all be algebraic points. And he proved that up to a degree, a given degree, you get only finitely many points. And that finiteness again came from a height bound. It comes from Northgate. He proved that these points have bounded height. But so he proves the theorem, but then he speculates that generally this bounded residual degree should not be needed to get the finiteness, that you should just get finiteness. And indeed, once G is at least 3, I think this does become a problem of unlikely intersections. If you have a curve in AG and you want to intersect it with all the varieties where you get an extra endomorphism, that looks exactly like this. You're intersecting a curve with things of codimension at least 2. So he speculates, he formulates that. And in the same paragraph, he formulates the André-Oort conjecture and also the version with Hecke orbits, the so-called André-Pink-Zanya conjecture. And now, a fundamental foundation of André's book and the basic work on the whole topic is Bombieri's 1981 paper on G functions, where he really puts this subject somehow in order. I guess Siegel had done much more on the E functions than G functions somehow. That wasn't in a very developed state. But Bombieri's paper the 1981 paper on G functions, where he initiated the local global viewpoint on these functions, and I should have said these were in the context of transcendental number theory. It's about studying the possible algebraic relations on the values of these functions. And here also the results are less satisfactory for G functions than E functions, but the key results you get in Bombieri's paper are that you do get bounded height for certain relations. Okay. So I met Enrico in 1988 when I came here to IAS as a postdoc. And my supervisor, Pila, had suggested that I discuss some Diophantine problems that Pila had raised with Enrico. And that led to collaboration, which was really great to work together on these problems. And these were some problems about lattice points on the dilation of a compact transcendental real analytic curve. But I want to state essentially a cognate result about rational points. So this was also 1989, actually. So let f from 0, 1 to R be real analytic. And by real analytic, I mean on a neighborhood compact set. Non-algebraic, meaning that there's no algebraic relation between x and f of x. And we'll call Z the graph. So this was about rational points on this graph, and the idea being that this graph is non-algebraic, shouldn't have too many rational points. And the theorem was that if you count the rational points on Z up to height h, so here h, this is just the naive height of a rational point, where the height of A over B in lowest terms is the maximum of the maximum of mod L and mod B. That this number is less than, for every epsilon constant, depending on Z and epsilon, h to the epsilon.
So you take height of both coordinates.
Yes, yes, exactly. And the height of x1, x2, or to xn is just the max of the height. We just take the maximum. So I returned to the Institute for 2002, 2003, and then I began to study extending this result to compact real analytic surfaces to go up on real dimension. At the time, inspired by Heath Brown's p-adic determinant method and by conversations with Enrico and Pila and Jean Bourgain. And then later so I worked on this for surfaces, but eventually this led to a much more general result in arbitrary dimension with Alex Wilkie. Where we take a set in R to the N, and instead of real analytic, we take something, well, definable in an o-minimal structure. So I won't give a formal definition of that. It includes higher dimensional analogs of this. So it includes the images of real analytic functions, which are analytic on the neighborhood of any compact box in R to the K mapped into R to the N. It includes also the full graph of the real exponential function, which is not of that form, and it includes all the sets you can somehow make out of those things and more things with Boolean combinations and including complements and projections and so on. It's a notion from model theory. I'm not going to say too much about that. It grew from model theory of the real exponential. It's somehow a model theoretic statement that the real exponential function is very tame. So now I have, so let Z Z is definable. So then the conclusion is, well, now you have to be a bit careful because although this set can be, I mean, one-dimensional set can be either analytic, can be either algebraic or not, but the higher dimensional set could be in total non-algebraic, but could have algebraic things inside. So we removed the algebraic part and got the same estimate. Now this algebraic part, by definition, is the union of all positive dimensional connected semi-algebraic subsets of Z. So this is connected positive dimensional semi-algebraic. So the idea being that the presence of many rational points in a high density sense on this set can only come from algebraic things. And as Enrico observed, then that this is closely analogous to the special set in Diophantine geometry and the sparseness of rational points outside it, as predicted by conjectures of Enrico for algebraic surfaces and more generally by Lang. How am I doing? Right, so this theorem had applications. So now I want to come back to the unlikely intersections, but this theorem found applications later to Diophantine problems of this unlikely intersection type through a strategy proposed by Umberto Zagna. And to illustrate it for the André-Oort conjecture, well, let's just say the point is actually, let's just illustrate it for the Manin-Mumford problem. But if you take the function exponential of 2 pi I s, which goes from C to C star, then the pre-images of roots of unity are rational points. And so now if you consider the Cartesian powers of these and a subvariety here, if you want to study roots of unity here, then you can pull that back and study rational points on some transcendental set. And that strategy actually can be made to work. Looks a fairly unlikely strategy, I think, but and also for the André-Oort conjecture when you study special points. So here, in the simplest case, you think of C as the moduli space of elliptic curves parameterized by their J invariance, and you parameterize that by the upper half plane and by the J function. And here, the special points correspond to quadratic points. And you can also make this same theorem work for quadratic points or any fixed degree. And therefore, if you want to study, if you have a subvariety of C to the n, and you can, right, so you have this fundamental domain, right, for the classical action of SL2Z. And it turns out that this J function is definable. So you do meet this condition, which is a non-trivial aspect in all of this work. Yeah, so then the way this strategy works is that the special point in general has or is supposed to have a lot of Galois conjugates, and those conjugates then become many rational or bounded degree points on your set. Yeah, so that's a strategy. So even for all the André-Oort conjecture in general looks like this. And this strategy can be applied. And in fact, it's the Galois orbits, which itself comes down to proving that the special points have small height. I don't want to go into it, but it's the height is again crucial. So, right. Because I now want to come back to the analog of this original problem, the unlikely problem, but in in a Shimura variety in a product of modular curves.
So this ZR that you just erased, can it be an infinite union?
Yes, yes, it can, yes. Yes, the standard kind of example of that is if you take a set like surface, a real surface Z equals x to the y on some even some x and y in some interval, then the algebraic part will have infinitely many components. But to return to unlikely, so this is now an unlikely problem. In C cubed, where now we view C as being the moduli space of elliptic curves parameterized by the J function. But we're going to consider exactly this problem. I'm going to take a curve in C cubed and I want to look at the set of points which are contained in a special subvariety of codimension at least 2. So I want to say briefly what they are. One way to be a special subvariety is if one coordinate is a singular modulus. And another way is if two coordinates are related by a modular polynomial. Those are the only ways. So the typical special subvariety of codimension 2, so in other words, let's say typically, we want to look for x1, x2, x3 in V with the property that 3 elliptic curves, one with J invariant x1 and x2 and x3, those 3 curves are pairwise isogynous. In other words, that the J invariants pairwise satisfy modular polynomials, and the conjecture, again, this unlikely intersection conjecture is that this set is finite. This set is finite unless the same condition essentially holds, unless V identically satisfies a special condition, that it's considered. Either one coordinate is constant and special, or it sits inside a modular surface. So this conjecture is open, so unless. So this is open, but there's a number of partial results, and via point counting and isogeny estimates and functional transcendence, it reduces to a suitable height bound on these points. Reduces to height bound. And what you essentially have to know is that the logarithmic height of all these points, if you have a point like this, that satisfies 2 modular relations, that the logarithmic height of the points is negligible compared to the degrees of the isogenies. So there's a variety of results, but I just wanted to come back to somehow the most recent results, that Dorr and Orr have brought G functions back into this. The G functions a la Bombieri Andre, and they can prove finiteness now under, well, they're still under conditions. I should have said, yeah, I did say that in Andre's theorem, you needed a point of multiplicative reduction. And they lack one here too. If the curve goes through infinity, 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 then they can prove finiteness. And other people, Papas and Urbanek. And I wanted to mention also Bignamini Massa, who can prove. So they can prove the Andre-Ort conjecture effectively for certain compact curves in AG, and all of this uses the theory of G functions and the results that go back to Enrico, and which give you these height bounds on where you have exceptional relations on these. Well, you parameterize these things by G functions. So Enrico's work has really had a profound influence here as all over Diophantine geometry and over so many areas that we're hearing. And it was my personal great privilege to work with Enrico, but also to have his guidance over many years. So thank you. I'll stop there. Thank you especially.
Thanks, Jonathan. Any comments, questions? Won't push Enrico anymore. I'm leaving you floor.
What are the, you have new problems? What are the new problems?
Me?
Also about proposing new directions, so.
I'm thinking about some new counting problems, actually. I mean, that instead of counting, well, trying to count not just points of bounded degree, but to somehow more count over wider sets, which should have some interesting applications. There's an awful lot of progress. I should have said I didn't go on this counting. I should have said there's an awful lot. I mean, the original result is very general, but it's sort of totally ineffective and sort of can't be effective in a general. But there's a lot of work on making it effective in suitable structures and reducing h to the epsilon to polylogs. That's industry. That's an industry, but it then also has implications to making Diophantine problems effective in good cases.
All right, so let's thank Jonathan again.